Okay, so then I'll just go to this decastly algorithm. Maybe I'll then maybe we'll just give some exercise. Okay, so now recastly algorithm. Are you seeing my polygon points here? What is the degree
Yes,
of this curve?
it will be 3, sir.
It will be 3. Okay, now you know how to draw this curve, and you know the equation of this also. But this guy decastly did a very fantastic job. Okay, what he does, okay, he does, let's say you want to find a point on a Bezier curve. Let's say at some parameter t. Let's say you choose something like 0.6 or whatever. Okay, now what he does is that okay, so at this point t, okay, t equals some value. Let's say on each of these line segments, let's say it's 0.6. Okay, you can come up with new points p0, p1, and sorry, b0, 1, b1, 1, and b2, 1. Between these 2 points, b0, 1, and between the next b1 and b2. And then this is basically linear interpolation or the linear formulation that we have seen before. Okay, between p0 and p1, you remember that equation, p0 and p1, we wrote that as p of t equals, okay, if you remember, 1 minus t into p0 plus tp1. Same form only all these are except in b's. So you have b0 and b1. Remember, b0 and b1 is used for b0 1 and b1 1 between b1 and b2 at some parameter value t. Okay, we can be consistent across all line segments that you are going to choose. Okay, this is the first step, and you can see these red points, and these red points will lead to you this shape. Okay, b0, and this is like a new kind of polygon. Okay, in this new polygon, you apply again the same linear interpolation like as shown here, same t value. Then you will get b02 and b12. Okay, between b01, b11, and then b11 and b21. Guys, is it okay?
Yes, sir.
Yes,
Are you
sir.
on
And
this
then we
page?
do the same thing
Yes,
again, and
so
we'll
then
get
we
the
do the
tangent
same
at the
thing
point.
for b01 and b11, and then okay, now we will go to the next step. You can see that you can generate, oh my god, something skipped. Okay, I think there is some skipping here. So there is one more line here in which, okay, I think it's that. So there is one more line that will come on this. That is what it is shown in the next page. Okay, where you have a line between b02 and b12, and then basically it's a successive linear interpolation. Okay, let me just pad this back. Okay, so if you see this further, okay, you can see that there is a b03. Okay, this b03 is what now? What can you say about b03?
It's just 1 point.
It is just 1 point on a Bezier curve at the parameter, whatever that parameter t is 0.6. Okay.
Okay, okay, sir.
So if you do successive linear interpolation of the original control polygon at that parameter, so you will get the point on the Bezier curve at this parameter. Obviously, you apply this entire procedure from 0 to 1, and that means you can get this entire curve here, which is actually the Bezier curve, and this is only a successive linear interpolation of that. Okay, we have not used anything more than this. So this algorithm is called as the recursive linear interpolation, or popularly called as the decastly algorithm. Is that understandable? Guys, can you post it? Any questions?
Sir, one doubt, sir.
Sir,
suppose we take t equal to 0.4, the b01, b11, b21 will all change, but at the end it will, that b03, another b03 will end up on the same curve as this b03.
No. I can draw the same thing here itself. Let's say you take these points as 0.4, right? Something like
yes,
this.
Sir.
Okay. Now you know that I am going to draw a thing like this, correct? These two are the ones. Okay, now you can see that I'm going to have another point, 0.4 here. And then if I draw this blue line here connecting them, and then you can see the point that it's going to lie somewhere here. Not this point and this point are different. Okay. So this will be a point corresponding to t equals 0.4.
So it won't be the same Bezier curve, no, sir?
Same Bezier curve. For see all the parametric ones. So how do you show that? It's the same Bezier curve. Okay, I have not drawn correctly here. Okay, it's basically if you see that it should go something like this. Okay, that's the correct curve. Okay, I didn't draw the curve exactly because this is more of
okay, sir. Okay, so that's all. So we can do.
Don't worry about drawing exactly here. Okay, this is my drawing problem, not the curve problem. Okay, so
sir,
the curve will be something. Yeah.
Sir, sorry
Yes,
to
Sir,
interrupt, but
so
your
we need
back is
4
about to
points
power off.
for.
So 1 second, I have to plug my Mac on that. Can you guys wait? Okay, so what is your question?
Sir, we need 4 points to determine the Bezier curve, no, sir. So
No.
we can have-
4 points will determine a Bezier curve for degree 3. You can have as many points as you want.
Yes, sir, for degree 3, sir. So we can use two t values and determine with along with B0 and B3 determine the curve, sir.
No, only one value of t determines 1 point on the curve. If you put another value, it will determine another point on the same curve, but with a different t value. Sir.
Okay, sir.
Okay, it will be different t value. Like for example, okay, if you go to this our usual Bezier curve here, okay, if I draw the Bezier curve, it will be like this. Okay, and that value t equals 0 here starting t equals 1. This value might correspond to probably t equals 0.5. Okay, this might be t equals 0.25 and so on. 0.25. This may be t equals 0.2. So each point of parameter t, you are going to get 1 point on the Bezier curve. This is a closed form solution in a sense, right? Or it's a you have a polynomial form equation on that. Okay, so something like this. So this entire t belongs to this curve and starting from 0 to and ending at 1. Okay, is that solve your problem?
Yes, sir.
Okay, other guys, I'm seeing only few guys talking. I think any others also pitch in. And at least put an yes on the chat box so that I see that you guys are all
Yes,
that.
sir.
Yeah, you can do that split into 2 Bezier curves. That's a good question, Gaurav. All that we can do, but a little bit far-fetched for our discussion today. Yes. For example, in fact, in the decastle algorithm is a wonderful algorithm. So in the same question that Gaurav asked, so if you keep on subdividing this using the decastle, what you will actually get at the final step is that let's say you have this t at 0.5 and you are doing the decastle algorithm, you will get this is the control. In fact, you will actually get this. Gaurav, are you seeing this picture? So you can see that this subset, if you divide it here, this subset will actually be another Bezier curve and this subset another Bezier curve. And you can see these control polygon points that directly comes out from the decastle algorithm. And you can split the curve. This holds good for any parameter t. Okay, you can split this curve and you can get Bezier control points using the decastle algorithm itself on that. I don't know whether other guys saw his question, but yes.
Sir, I have a doubt. So the point of the curve at t equals 0.5, can we find that point by taking the like how we find the centroid of a triangle? Can we do that here?
You can use the decastle algorithm, it will do, or you can use the our polynomial Bernstein basis. Either way you can do. But the one good thing with the decastle algorithm itself, your B01, your B01, B11, subsequent, like if you go to this curve, that the last one, it is very clumsy. Okay, I'll go back. Okay, now if you look at this curve, okay, now you can see this guy, and let's say you are subdividing at this point. Okay, that means what will be the control polygon of this side of the curve? It will be like this. Okay, and
Yes,
then
sir.
the other control polygon will come from here. Okay, this one and this one and this one. Remember, this all degree 3 curve. We are splitting the same degree 3, and you see there are 4 control points for this side of the curve, and then there are 4 control points coming from this side, and you can see that. Okay, these will be same, and this will be collinear here. Okay, but at this point you are splitting. So you can see that the decastle algorithm, when you do that B01, B02, it will actually directly give the control points for the split curve on that. Okay, and similarly the other side of the curve, you can directly get the control polygon, which is not the same thing if you use the polygonal, the binomial form or the Bernstein basis form. There also you can get it, but you have to do more work on it. But this decastle guy will directly give you the control polygon points for the subdivided curve also. Any other question? Is it becoming
Actually, I have a question on this. So basically, if I have to program this, I was wondering maybe you might have already covered this, but what is the stopping criteria for the recursion? So when do I
Okay.
stop?
Until we
See,
get 1 point, sir.
see, each time you are you are going to vary the parameter. See, you can either go for recursion, okay, and you have to end at see, there will be a starting parameter and then an ending parameter on it, okay. So you calculate this guy for every t.
Okay.
And then your stopping criteria will depend on your n.
All right.
Because
Okay.
you can
Yes.
guess that you can see for this guy n equal to 3, right? So how many
Yes.
times you have subdivide this polygon? You can see that one time, and then this is second time, and then this is third time, and then fourth time is what you are going to get a point. That is again exactly same as 0, 1, 2, 3 steps.
Okay. All right.
Okay, guys. So that will come from your degree of your or the number of control points, so to speak. You don't give the degree as input, but the number of control points, but starting from 0 and then ending at n minus 1, which is the n is the degree of it. So we use the term n itself here on that. Okay, now you can stop the recursion once it reaches your thing, or in the other way, if you are starting from up, you can go to down, either way. Is that answer your question? Yeah, that's a good point. Yeah.
Yes. Yes. It answers
But
that.
in recursion, you can go to loop also, right? All the recursion, you can go to loop. So more safer way of programming, because if you are not familiar with recursion stopping criteria or how does a recursion stops, then it's a problem. Okay, so rather than that, you convert this into a loop. But again, it will number of loops you have to determine where you are going to stop the loop. But at least recursion is little bit more difficult to understand for many of the first time programmers, or even possibly some of the seasoned programmers. Okay, nice point. But on the other hand, okay, you can also implement this same Bezier curve via your Bernstein polynomial. Okay, so what will be the difference between this and that? I mean, all guys, can you post something, please? Because only few guys are interacting with me.
Sir,
So
one
what do you
doubt,
think
sir.
will be the difference?
Sir, if we use the algorithm, we will get a discrete set of data points. But if we use the function,
Even
we can
here
just
also
plot
it's
it.
discrete only, right? You are going to compute t equals 0, t equals 0.1 or 0.01, whatever. See, finally there is a linear approximation when for a display. That's only for a display purpose. But if you go to t equals 0.00001, still you can compute point on the Bezier curve. So the resolution will depend on what is the resolution on the increment in t. And that holds good either it's a de Castley or it's a Bernstein. So time complexity, I think I would give that as an exercise for you. This is only a linear interpolation. All you need is only one function, which does the linear interpolation in terms of your de Castley algorithm. So how many times it gets called? Well, you can consider them as constants. Then it's overhead only on the number of computation, which could be O of n in that case. I think practically also it may behave something like that. Actually, I haven't tested it. That's a good point.
It
Now, if
looks
you use
like a
Python,
linear complexity algorithm.
True, correct. Yeah, but it's all depends on the implementation, how efficiently you can do all that. So the implementation can also mess it up. Then your running time can see, that's the difference between your big O notation and then actual running time on the system. Okay, there is still, you can see there may be still a difference depending on how you implement it efficiently. Okay, so but what is the difference? If people have not answered, suppose you implement this with de Castley and implement this with Bernstein, what are the other issues or potential issues that you can think of? Okay, I'll go to that equation. Now you tell me whether. Okay, now this is the equation here. Now you tell me what could be potential issues.
Sir, over here we have to find the polynomials, sir.
Correct.
Over there we are just
But
linear
that is also
equations we are finding.
multiplication only, right? Any problem that you see?
Sir,
No, sir,
are
but
we taking
in the
inputs in case of de Castillo?
Same inputs B0, B1, B2, B3. Same control points as the input.
Okay.
See, once you have the control points, see, remember, okay, one thing maybe I didn't tell. See, control points are always given in order. Okay, what does that mean? Okay, so let me tell this. Okay, so if I say 3 points here, okay, okay, if I do this as B0, B1, B2, you get to another one control polygon, and the curve will be according to that control polygon. Okay. Whereas, okay, that means, let's say, whereas if I name this as, okay, I should go to another color. Okay, this as B0, and this as B1, and this as B2. What is the implication? So remember, now in the second case, this is the control polygon. The curve will be like this. And in the first case, this is the control polygon. Curve will be like this. So the order matters in which you give the control points. Okay. So that order you have to set, and the curve behavior will be according to the control polygon points that you give as input. And that is very important. Guys, are all you there? I mean, no feedback?
Yes, sir.
Yes, sir.
Only very few guys. What happened to all other people? All are you there? Can you just put a quick yes for me to show your presence? I saw only 11 guys. So all others have gone for coffee or tea, or somebody said, what is it, couldn't do, or okay, other guys put an yes. I saw only 14 or 15 guys. All other guys are there or not there? I didn't get yes from all people, I suppose, who are attending it. Can other guys also respond or gone into sleep mode? So any other question here so far we see? So it is becoming too much. You give me some feedback on that. So you want to go for some 5-minute break, something like that, 5 to 7-minute break, and then we'll reconvene. Because I have a lot to cover, then I have to give some on B-spline curve. But in the afternoon also, I'll give you some exercise. But in afternoon also, we may have a little bit see some something on surfaces. As you might have guessed, all these things are involved in terms of programming and so on. And you can, of course, I gave you some Python code, which gives only basic curves and surfaces. So do you want to go for a break now? Some 7-minute break? Are you guys okay? Okay, a break would be nice. That's fantastic. So maybe Aditya, maybe you can stop the recording. I think doing the recording.
Yeah, sure.
So we'll reconnect. So in my watch, it's n minus I. What is n? It is I goes from 0 to n, right? So if you go to this n minus I, when it could potentially go to 0. Like for example, you are starting with I equals at some point of time n equals 2, I also equals 2. You can see
Possibly there is a network issue at Dr. Ramnath.
Okay, I thought it happened on my end.
It's confusing.
okay,
really
so
know.
guys, I think there is a network problem from my side. So what I'm trying to say, are you back?
Yes, yes.
Yes.
Okay, I think I had. So now the thing is that this n minus I can go to 0 factorial somewhere. Okay,
All
because
right.
n can be 2 and I also can be 2. It can go to 2 minus 2. So now we have to have some mechanism to deal with this guy. Okay. So potentially that is the problem, and also of course that special conditions, and so robustness wise, the de Castle algorithm is much more robust implementation wise.
Okay, all right. And
Okay.
I mean, there is one more thing, like when we use these factorials, we can only go for very small number of n's, because
That's what I was about to say. Yeah, that is
Yeah,
about to
please.
say. When n becomes larger, you have to have long
Yeah.
int and other things coming
Yeah,
in.
exactly.
Nowadays, the factorial is implemented with long int. I mean, normal int itself is little too much. Yes, the factorial also needs to take care of long. In fact, we have to implementing with long int now, I think.
Okay, okay.
So that is yeah, that's a very good point which I was about to touch, and you mentioned that, right? So that is the reason. Given of course this might be, if it's this is a simple multiplication in that case where you don't have to think about looking at the code in the recursive manner or loop manner. This is very simple, straightforward writing of the code. It's a multiplication, and but if you are not careful, this code can come out. It can break. That's the problem. So you have to add-ons, and then as you said, the factorial is another issue, and then long int is what typically now used for factorial. Okay, that's very nice point. Yes. So if you compare these two, I would say de Castley algorithm.
I think another network issue.
I think my internet is also having some trouble now.
Yeah, we can hear you now.
Yeah, I mean, I'm actually using a institute network only, and
Okay. So another point, at t equal to 0.5, the Bezier curve point will not be the centroid of the control polygon.
no, not required, or not always. Some cases, yes. In some special cases, it can be, but definitely, I don't think so. This is not
Because the
this.
basis function values are not the same at t equal to half.
Yes, correct. So yeah, so if you look at the behavior of the basis function, we can answer many of the questions from it. You're right.
Thank you.
In some cases, we may arrange the polygon control points in such a way that it passes through that. But yeah, this is see, the whole idea. I mean, in my opinion, with what I have understood is that except in some design cases, it's more like we don't want this to constrain to certain paths much. But we'll also see, like I think we had some cases, interesting design cases, where we had to develop something. And as far as I could think of, only the B-spline, in my opinion, was the only solution to design that. Okay, other things I don't think we'll be able to do that, but I'll show that in some cases we may have to create some instances where it has to pass through certain points. I'll try to elaborate on that.
So I have my bachelor's in electronics and communication.
Okay. This is an independent of. I just asked. So my problem, you see this screen, right? This blue color screen, this thing. So this guy should appear on the entire screen. You see this bottom XYZ. Yeah. So this should actually appear on the entire screen of this blue. But it is not happening because it's supposed to be a high resolution screen. What this high resolution screen does it to make it 1/4 of the display. Okay, this is a new problem, it seems. I don't know how to, unless your software itself can adapt to that high resolution, it seems that you may have to face this issue. That's the reason why I want to do it on the other system. But if there any fix on that, I tried something, but it couldn't fix that issue. That's the problem.
Can we try now to maybe move to your other system?
Okay, maybe yeah. So yeah, the other system is also running. So can I just log in my other system briefly?
Right, sure. Just maybe ensure
so
that
will it allow parallel one WebEx or no parallel is possible?
It will allow as far as you use a different email ID.
Okay, so let me try that. Let this be on.
Exactly.
I'm going out of WebEx. So maybe sharing probably we cannot do from both. So I'll try to go to the other system, and then I'll see if it is because the other one is better.
Because at least for a brief moment, both of your systems were available in WebEx. You had joined in both systems. And
yeah, and after that I switched off one of them. Actually, I switched off because The
Okay.
problem was in the using the mic. I'm not using an earphone. So
No, that's okay. We will, from our end, I can mute one of your.
okay, that will be good. Yeah, that will be good.
Right.
Okay. So let me try this.
Sure.
So it is starting the meeting there. And I tried to fix this problem, but I couldn't do it. I mean, I tried it in 4 or 5 different systems, and it wasn't working in others one. But unfortunately, okay, let me try to join here. I'll switch off the mic here. Okay, so now can I, what should I do now? I'm in both systems.
I think you can stop sharing your screen from the current system.
Okay,
and
I'll
then
try
share.
that. Stop sharing. Okay, I'll try that.
Yeah.
Okay, I'm now stop sharing this one.
Right.
Okay, I'm actually, maybe what I will do is that, is there any echo?
No.
Okay, what I will do is that I will use this, share this screen and speak from the other system itself. I'm not unmuting this.
That's fine.
Okay, so the video and audio comes from the other system. I'll just share this guy and see if it is okay.
Right.
It might be a little better.
Yes,
Are
I
you
think we
able to
can
see
see
my
your
screen now?
Yes.
Okay. I
Yeah, the
think this
audio is
dual thing is
also
better.
working. Right, right. The audio is also working. There's no echo.
Pardon?
There's no echo as of now, so should be fine.
Okay, I think what I can do is that I can, okay. Now can you speak? Well, let me see whether I can hear you.
Okay. So yeah, at our end we have no echo.
Okay, I have kind of switched off the, muted and volume completely reduced in one system, but that is where I'm sharing the screen from. And I'm from, okay, now I'm also able to see this parallelly. Okay, guys, all of you are back. This is great.
Sir, how did you manage to increase the resolution of the, sorry, increase the window size of?
No, I'm not doing that. That's why we did. We are using two systems now. One is that I'm using my old system to demonstrate this, and that is where I'm sharing from.
Oh, sir, so your old system doesn't have retina display.
My old system doesn't have a retina. It's a very old one. Pre-retina days. This is like a 2008 system or something like that. Okay.
So because I'm
Now,
also using Mac, and in my Mac, I have retina display, so it's showing me a very small screen.
that is what that's what I showed you in my previous case, right? In my previous case, that's the same problem. And that is called as high DPI problem. You check for high DPI. Okay. That didn't solve the problem though for me, unfortunately. I know why the problem is happening, but I don't have a solution to solve this problem. So one step ahead I'm there, but not completely. Okay. So if all guys are back, I think this would be a good way to for me to demonstrate. Okay, so let me go to curves here. Okay, and okay, the interpolation also. So there should be some more buttons that's missing. But if you see this interpolation here, I'm going to click. Hope all guys are available now. Okay, I'm seeing. We can see that there are points that I'm doing it. So this is not a Bezier, by the way. This is some interpolation. I don't know what that interpolation is. Possibly. Okay, now this is the curve. Let's say. Okay, now I can see that if I increase the order or a degree, you can see the curve behavior is erratic. Okay, this is not Bezier though. Okay, so if I say okay, you can see the curve behavior is very oscillatory on that. Okay, so this is the normal interpolation. I don't know which interpolation he uses. Some interpolation method. Okay, now okay, let me just try to cut this guy. Okay, now I'm going to do Bezier, guy. Hopefully all are back on that. Okay, we'll go to this Bezier tab. Okay, now I'm going to draw the Bezier. Okay, I can see that 1, 2, 3. You can see the Bezier curve also as I keep on drawing the control polygon points. Are you guys observing that? give some vocal feedback?
Yes,
Yes, sir.
Okay, now we can see that the Bezier, what will be the degree of this curve?
So it will be 3. 3, sir.
3. I am pointing another point. You can see that. One more point, and you can see one more point I'll put here. Remember, the curve closely follows the input set. Okay. Okay, now you guys observe carefully. I'm trying to do something else. Hopefully it works. Okay, now I'm pulling one of the points. Are you observing that?
Yes, sir.
Now what will happen? What happens to the curve?
The curve also gets pulled.
But does the full curve gets full, or some only part of the curve gets full, or
The part that corresponds to the point that you're pulling, sir.
Okay, so that is actually not true. Maybe it's not very evident in this. So when you do this pulling here, okay, so you can see this actually entire point gets changed. You have to observe very carefully. When I pull this point, again, you can see here, almost all of the Bezier curve gets changed. Okay.
Oh,
I mean, except this, you can see slightly somewhere here, it's not changing too much, and probably somewhere here. But barring that, you can see that you can see this even here, observe this portion on the left-hand side, that also changes. Okay, you can see that changes. Okay, so this is, I think was Aditya was asking, this is actually one of the disadvantages of the Bezier curve. Like if you look at the basis functions, okay, did you remember the basis functions? Okay, if we don't go to the full mode, I don't know what will happen. So if you go to the basis function, you can observe that at other points, all the basis function plays a role. That means your entire curve gets, if you look at any of the other parametric points, t equals some ti, all basis function has some value. Okay, are you able to see my mouse pointer or not? Okay. So if you see that, that is the reason why even if I move any other point like this point here, okay, actually the entire curve gets affected. Okay, so this is the disadvantages of, or one of the disadvantages of the Bezier curve, where I don't have a local control. It's only a global control. I mean, I still see it's intuitive, right? You can observe that it is intuitive. Correct. So you can observe that it is intuitive, the changes are happening intuitively, but there is a global change happening on this precisely because of the basis function behavior on it. So every guy gets affected. So what is the other problem? What is the other disadvantage you can think of? Hope all guys are there. I'm not alone. I'm not speaking alone. So what could be the other disadvantage? I myself confused on which terminal I am in. Okay, I'm supposed to do in the chat here. Okay, so what do you think the other problem is? Can you guys quickly throw some light? Okay, I'll give you one more hint. Okay, now I'm putting another point. Okay, what is this degree of this current curve here?
5, sir. No,
Okay,
sir,
now
6.
it's okay, 5 or 6. Okay, 1, 2, 3, right? 0, 1, 2, 3, 4, 5, 6. Okay, this is 6 maybe. Now, if I add another point, what will be the degree of this curve?
7.
So what it is? What can you say now? So the degree of the curve is closely associated with the what?
Number of points.
With the number of input control points. Okay, so that suppose can I get, even if I have 7 or 8 control points, can I get a degree 3 curve? Is it possible in Bezier?
No, sir.
Sir,
No,
sir.
it is not possible. So the degree
Unless
of
they
the
are collinear.
yeah, if they're collinear, we can do it, sir.
no, collinear simply tells you the curve looks like a line, but what will be the degree of that line? Okay, let's try it. The degree of the line will also depend on the degree of the control point. So it has nothing to do with whether it looks like a straight line or not. Okay. So suppose if hopefully I can give a collinear one. I don't know my panel. Okay. Now if I keep doing this, See, this is a 4 control point and it's all straight line. Bezier is still a straight line. But what is the degree of this Bezier curve? There are 5 control points. So for 0, 1, 2, 3, 4, right? What is the degree of this Bezier curve?
4. Okay.
It is still 4, even though it looks like a straight line. But if you look at the equation, it is still 4 on that. That is one thing that we don't want. Or is there any way that we can get out of this? But of course, if I do
Sir,
little bit, yeah.
how can a degree 4 curve look like a straight line, sir?
That is a very so, but this is a straight line only. You saw that, right?
I
So
saw that,
basically,
sir, but
what
it's
happens
hard
is that
to.
if you do an interpolation, see, you now look at a decast form. Okay, now look at the answer. Maybe a little bit easier to visualize from the decast form. So you look at this decast right? Where is that?
Can it be like that as the points
So
are
if you
collinear?
do
So
successive interpolation, where it will happen? Like you are doing successive interpolation here, right? You are seeing my screen.
Yes, sir.
Okay. Now, if all these, let's say B0, B1, B2, B3 are collinear, where the successive interpolations will lie after the end of it at the last stage?
It will lie on the line, sir.
It will lie on the set of collinear lines.
Yes,
Okay,
sir.
so your Bezier curve will also be a straight line there.
So that's okay, sir. But the degree of the polynomial,
You
how
can
can
have,
it be?
a higher degree polynomial generating straight lines also.
sir,
That looks
can it be
little
like
first. So
sir,
what
can
you
it
have
be
to
like
study is that based on that you have to study the slope. If you just derive it, you can see that the slopes will be constant and so on. So it has nothing to do with the degree of the curve in that sense. I mean, we are all used to, y equals mx plus c for long. Okay, and maybe that is the problem, that it is preventing us from seeing how a straight line can have a higher degree also. Okay, so in parametric space, there is another book, maybe I'll let you to see in Martinson, there is a good explanation of this aspect of the thing. Okay, which, but you can observe that the guy is looking, okay, straight line on that, which is a higher degree straight line on that. Okay, whether we like it or not, or whether our y equal to mx plus c is keep coming and haunting us here, okay, that might be the case on that. Okay, other than that, it can still very much happen on that. So if I put everything on one guy, it's definitely a straight line only. But you can see the degree from our explanation, the Bezier degree has to be definitely not 1, right? More than 1. Okay, so this is, of course, it may be a fascinating one, not generally used in practice, but in some instances it is very useful. But suppose, okay, now I'll give you one idea, one thinking on that. Okay, now let us say I move this point out of collinearity. Let's say the last point out of collinearity. Something happened. I'm just trying to pull the first point or the last point. Let's see whether I can pull that. Okay. Now you can see that the straight line is kind of diverging a bit on that. This also can be explained via the decast algorithm that you are trying to get. Now, if you pull one more point, your entire thing is out. Okay. So did you guys observe?
I have a doubt, sir. In the previous in the previous case where you just used
Yeah, so
inbuilt,
Aditya's answer, it can be square or even cube or any other degree actually. So
sir,
that is what explanation on it. Yeah.
sir, in the previous interpolation that you did without the Bezier interpolation, you showed that by increasing n, the
Oscillations are higher.
increase tremendously.
Correct.
Sir, but does the variable n correspond to the number of points in that, or because you?
No. I think, yeah, it will be number of points there also. But in that case, now even number of points, you can have varying degree of this. One you want to have more degree in some cases, and some cases you don't want more degree one. See, more degree means you can compute more of the properties and it won't break down, right? So certain times you need more degree one. Okay. But in some cases it's not. But the whole point is that when you have those set of points and try to increase the degree, okay, your oscillations come into picture, okay, which is not really good in terms of designing something. That is the whole point.
Sir, my doubt is how can you keep the number of points constant and then increase the degree?
It will depend on your interpolation scheme on that. Okay, some of the interpolation may allow that, but of course, yes, it's like it's maybe difficult to see in practice. So if you have 10 points, if you want to interpolate all that, naturally the degree of the thing is more. Okay, you are right. But what I'm trying to say is that as you keep increasing more number of points, the oscillations are going to come into picture. That is the whole point.
Oh, okay, sir.
Okay, but we will see in the B-spline, we can kind of disconnect this degree of the curve with the number of control points that we are going to see. But another point here I would like to mention, even though the degree is high, okay, we of course don't pass this Bezier curve to go through every point. But even in that case, you can see the oscillations are almost null. Okay, there are no oscillations that are coming into picture.
Yes, sir.
Okay, so that is, you're right. I mean, as you increase the number of points, your degree of that interpolation also going to change. But that is not the only problem, but it there's an effect on oscillation also. That is my point on that. You are right in terms of interpolation in terms of number of points. Okay, so any other
in B-spline interpolation, the degree and the number of points are disconnected. They are not dependent.
that is in B-spline. So I'll touch B-spline now. Are you guys ready for B-spline? I think some of them are completely absconding, I think.
Yes, sir.
Okay, so I'll probably briefly, and I won't go into that much detail of this B-spline curve maybe. I don't have pen connected to this guy. Okay, maybe if I'm a little bit scared. So what I will do is that I'll stop sharing this screen, Aditya, and then I will share the other screen. Okay.
Okay.
Sorry for that goof up, but okay, I'll share the screen now. But I think we found a way, and very interesting. Okay, I never realized that we are going to find a way from this. Okay, now guys, you are able to see my, GUID is in high resolution, so it has gone out into a problem mode. Okay, let me go back to my presentation. I think this is great. Yeah, I didn't even realize we could do something like this. Okay, now you will go to this B-spline, but B-spline also is going to use the same number of input in terms of control points. Okay, so control points and control polygon terminology is going to stay there. Okay, what it is going to be little different from what we have seen in Bezier. Of course, it's going to get more complex. Hopefully, some guys are also listening who are not getting any feedback.